Now we will see an example number 14 of textbook. The information is given that a book with many printing errors contains 4 different formulae for the displacement y of a particle undergoing a certain periodic motion. Then they have written 4 equations. So first equation is given by y is equals to a sine 2 pi t over capital T. Now in dimensional formula we also remember one more thing, that if the equation is represented by sinusoidal function, that means it is sine, cosine, like that, then whatever the term of theta or angle, it is dimensionless, or it should be dimensionless. So here in the angle term with sine, we can say that here this bracket is a theta and it should be dimensionless. If there is any dimension inside it, then we can say that this equation is not true. So here for the first part we will find the dimensions. In a left hand side they have given the displacement. So LHS is m0 L1 T0, while in RHS they have given that A is maximum displacement. So we can say that it has dimension of L1, but here we have to check that whether this bracket has any dimension or not. If it is dimensionless, then the equation is true, but if there is some dimension is found inside this bracket, that is in terms of theta, then which is not possible, and at that time we say that this equation is wrong. So for that we will find that the dimension of numerator, that is 2 pi t upon capital T. Now here 2 pi is dimensionless, but t is obviously time, so it has dimension of time, that is t1, and in denominator that is a periodic time, so that is time of period also has a dimension of time, so it cancel each other's effect, and therefore ultimately it becomes t0, and therefore the first equation is correct. Now we will compare it for the second equation. In second equation they have represented it with y is equals to a sine v into t. Here they have explained that v is a velocity and t is a time. So now we check the dimension of v into t. So we say that dimension of v into dimension of t, it should be 0, it must be 0, but here we find that whether it is 0 or not. So here we can say that it is m0 L1 t minus 1 into it is t1. So ultimately it has dimension m0 L1 t0. Now here there is a confusion for some students. Here this is the dimension of this angle, this portion has this dimension, this is not the dimension of A only. So here what will happen, sometimes we found that here in left hand side it is a distance or a dimension of length. So here in this sine theta also we got the dimension of length, and therefore we are forced to think that this is true, but no, here we know that the sinusoidal function has never any dimension. So in this equation of this sinusoidal equation, that v into t must be dimensionless, but here it is not true, here it has some dimension, so it is not dimensionless. And therefore we say that it is not true. So this is wrong equation. So equation is wrong. We can say that equation 2 that is given is a wrong equation. Now we will check for the third equation. Now this seems to be easy question for all of you. Now in third question, what we will have to find out again in the same manner. We are given y is equals to a over t into sine t over a. Now again we should have the equation of sine theta must be 0. So here we compare it again, that t upon a, but obviously t has a dimension of time while a is a distance, so it has a dimension of length, so it is like t1 l minus 1. So again t1 l minus 1, so it is again not dimensionless, and therefore this is wrong equation. Here another part is also there, that in multiple part, that is a by t is also dimensionless, that should be having a dimension of length, but it is not like that. It is having a dimension of length and time as it is given in the sine term. So this is some confusing term. Sometimes we found that okay, here sine t by a has a dimension of t1 l minus 1, but the rule is that the term which is in a multiple with a sinusoidal, that is sinusoidal angle, is a dimensionless. So here t upon a must be dimensionless. So ever if we found this is having some dimension, we strictly say that this equation is not possible. Now we go with the condition 4 of the formula. It is given that y is equals to a upon root 2, then it is sine, it is given that 2 pi t over capital T plus cos 2 pi t upon capital T. So now again we have to find out whether here the sinusoidal term has a dimension or not. If they are having any dimension, then we say that this equation is wrong. So for the first part, we say that it is 2 pi t upon t. Now it is also like first equation, in which upper part has a dimension of time 1, lower part also has a dimension of time 1, and ultimately it is a dimensionless. So this is possible. Now then we see that the equation in right hand side, the first term, that is a by root 2. So obviously root 2 has a no dimension and a has a dimension of length. So LHS is obviously having a dimension of length, and RHS also has a dimension of length, and therefore this is possible. So this is true equation. So this equation 4 is true. So here we can say that which equations are true. So true equations are given 1 and 4, while wrong equations are given, that is 2 and 3. So these are the information of the example number 14. What is written there in example number 15? It is also an interesting case. It is given that a famous relation in physics relates moving mass m to the rest mass m0 of a particle in terms of speed small v and the speed of light c. Now this relation first arose as a consequence of a special theory of relativity due to Albert Einstein. Now a boy recalls the relation almost correctly, but forgets where to put the constant small c, that is the speed of light. So he writes equation as m equals to m0 over 1 minus v square raised to 1 half. Now we have to guess where to put the missing c. Now this question is again not that difficult one. We can simply apply here. According to the principle of homogeneity of dimensions, powers of m, l and t on any side, that is on either side of the formula, must be equal. Now for this, on right hand side the denominator has the term 1 minus v square raised to 1 half. It must be cancelled out because left hand has a mass and right hand has a in a numerator mass. So the denominator term must be cancelled out. So obviously we have to put somewhere it the c so that it cancel out, and therefore we can say that the c replaces the value, that is m equals to m0 over 1 minus v square over c square raised to 1 half. So this c must be replaced at this point in this equation. So this c is replaced, and therefore we have written that equation m is equals to m0 over 1 minus v square over c square. So see, here these dimensions are cancel out each other and this term becomes as it should be. So this is the correct true equation for the rest mass as per as Einstein's equation. Now we will see another example, that is example number 19 of the textbook. It is a large information given on the question. The information is like that: the principle of parallel or parallax in article, it is used in the determination of distance of a very distant stars. The baseline AB is the line joining the Earth's two locations 6 months apart in its orbit around the Sun. That is, the baseline is about the diameter of the Earth's orbit, that is 3 into 10 raised to 11 meter. However, even the nearest star are so distant that with such a long baseline, they show parallax only of the order of 1 second of arc or so. A parsec is a convenient unit of length on the astronomical scale. It is the distance of an object that will show a parallax of 1 second of arc from opposite ends of a baseline equal to the distance from the Earth to the Sun. So how much is the parsec in terms of meters? So here first of all we must write down that the length of baseline, that is distance from Earth to the Sun, and that is called astronomical unit. So first of all we will apply the information. We say that the distance of baseline, so length of baseline, we say length of baseline that is equals to distance between the Sun and the Earth, and this distance is called 1 astronomical unit, and it is also written as 1.5 into 10 raised to 11 meter. So this is the unit meter. Now parallax angle is given as a 1 second. So we can say that parallax angle theta is 1 second, that is also written as 1 minute upon 60, and it can also be written as 1 degree upon 3600. So in the earlier lecture we have determined it, and it can be written as that theta is equals to, degree can be converted into radian as pi over 180 into 1 upon 3600. Now when we solve this, what should be that distance? We have to find out that distance r is a 1 parsec, that is what. Now obviously from the figure we can draw the simple figure that L, this distance, here I draw the distance, so here I draw the distance that is given. Suppose these are two stars are there, here they forms angle with given point of observation. Say this is the point of observation and this is the condition. Now we can say that angle is equals to arc upon radius. So if this is baseline L and if this is radius r and if this is theta angle, then angle is equals to arc upon radius, and therefore therefore we have to find out this r. So to find out this r, we can say that therefore r is equals to L over theta. When we can simplify it, we can say that therefore that r is equals to length, that is astronomical unit 1.5 into 10 raised to 11, and theta is given, that is pi upon 180 into 1 upon 3600. Now when we apply it, we found it to be 3.1 into 10 raised to 16 meter. So here we simply say that 1 parsec or 1 parsec is a distance that can be written in a meter is equals to 3.1 into 10 raised to 16 meter. So this is your example number 19, and it is also very important one. Now we will take the next example, that is example number 20. In this example number 20, we will given and we will apply the information again in the same manner that is given regarding parsec. The nearest star to our solar system is 4.29 light years away. Now how much is the distance in terms of parsec, and how much parallax would this star show when viewed from two locations of the earth 6 months apart in its orbit around the sun? Now as per as the question, first of all we say that the distance is given as a 4.29 light year. So here suppose x is a distance that is given, that is 4.29 light year. Now first of all we must know that what is 1 light year, that is 9.46 into 10 raised to 15 meter. That is the distance travel by the light in a 1 year. So that is given by 4.29 into 9.46. So this is 9.46 into 10 to the power 15 meter. Now this is turns out to be in meter. Now suppose I want to convert it into parsec. So to convert it into parsec, what I need, that I need to divide it with 3.08 into 10 raised to 16 second. So it is called, or it is converted into parsec. So this is divided by 3.08 into 10 raised to 16. So this turns out to be as parsec, and that will be around 1.323 parsec. So this is the first answer. Now they have asked us that if it is viewed 6 months apart in that solar system, then obviously in 6th month we can say that the distance would be like this. Suppose this is the sun, right now suppose this is earth, so we fill it with, say this is sun, say this is sun, it is filled with orange color. Say this is earth, it is filled with blue color. Now in 6 month span it would cover like this. In a initial, if it is at right hand side, then at final stage it would reach to the left hand side in this manner. So in the time of 6 month span it will move in this way. So this is t equals to 0 month. Then we can say that if it is moving in this direction, then at t equals to 6th month it would be somewhere here. Now this distance, this is sun, this is earth, so we know this distance as 1 astronomical unit. So in 6th month it will cover another 1 astronomical unit. So as a whole it will be 2 astronomical unit distance that it will cover, and obviously the x that is given as a 4.29 light year. So how much angle would be there, that we will get in a terms of parsec. We can say here that theta is equals to L over R. Here L is nothing but 2 astronomical unit and R is already defined as 4.29 light year. So 4.29 into 9.46 into 10 raised to 15 meter. So this is the term that we can apply, and when we apply it, what we will get, that is 1.512 second. So the angle would be very small, but this can be explained in this manner. Now we will see the next example, that is example number 24. Now in this example we are given a very simple information. This is also done previously. This type of example is done in our earlier lecture, but this is the last example of the exercise. What is given there? We can say that when the planet Jupiter is at a distance of 824.7 million kilometers from the Earth. 1 million means 10 to the power 6. So if it is 824.7 million kilometers from the Earth, its angular diameter is measured to be 35.72 seconds of arc. So to calculate the diameter of Jupiter. So in question number 24, what they have given, it is clear that this is suppose Earth, this is suppose Jupiter. Now we are observing its diameter, and we found here this is diameter or angular diameter of the Jupiter that we have to find out over here. So what we will do to find it? So here from this we can simply apply that we are given R, and this R is given as 824.7 million kilometers, that is 10 raised to 6 kilometer. So one thing is given. Second, they have given us theta. So theta is provided, and that is 35.72 second, that is 35.72 divided by 3600 into pi upon 180. So this will be converted into radian, so it will be in a radian. And now we have to find out the diameter D. So now what we will do, we will calculate it with the help of the information given here. We can simply write that D, in this case D is equals to, because our equation is clear that angle is equals to arc upon radius, and so D is equals to R into theta. We are given both things. We can say that 824.7 into 10 raised to 6 into 35.72 over 3600 into pi upon 180. So now when we apply this, we can calculate the term, and we found that this distance is to be 1.429 into 10 to the power 5 kilometer. So this is the angular diameter of the planet Jupiter as given information. So this is the example number 24 of exercise. Here this example is completed.